Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last lecture, we have been talking about a very challenging phenomenon which is CC bond activation reaction. And we have looked into CC bond activation reaction in the pretext of CH bond activation or HH bond activation. And what we had seen is that CC bond activation reaction is very challenging as compared to the other kind of bond activation reactions. We have also discussed about the reason for CC bond activation reactions being more challenging than CH and HH bond activation reactions. We have also looked into the mode of action of various CC as well as CH and HH bond activation reaction. What we have done in the previous lecture is also we have drawn a parallel between cyclopropane ring and alkene, and what we had seen that for the CC bond activation in a cyclopropane ring which is given over here as opposed to a CC bond activation in a alkene where it has a alkene has a double bond. What it was shown that this ligand to metal sigma donation affects the sigma bond of the cyclopropane, which is sort of bent because of the orientation of the orbital, whereas a similar composition of CC bond activation between a metal orbital and the pi cloud of an olefin does not affect the sigma bond, which sort of remains untouched, whereas it does affect the pi bond. So, there is a sharp distinction in the difference between CC bond activation of a cyclopropane ring containing a sigma bond versus CC bond activation of a alkene containing pi bond. Similarly, the back donation metal to ligand pi back donation completely cleaves the CC sigma bond of the cyclopropane, whereas in the alkene case the back donation only happens at the pi star orbital, thereby cleaving the pi orbital, and the sigma CC sigma orbital remains sort of untouched. So, what we saw is that CC bond activation reactions having two different effects if it is done on a strained ring like cyclopropane as opposed to that of an alkene. And some of the examples that we had covered in the last lecture about various types of CC bond activation reaction, the commonality that ran through all these examples were the fact that these systems where CC bond activation occurred, they were highly strained, and as a result of CC bond activation the ring strain got released favoring the forward reaction, and same is true for the cyclopropane ring which is highly strained. However, when it undergoes CC activation, there is a release of strain when and it gives a metallocycle with release of strain which resulting in the stability as well as the forward reaction of cyclopropane in resulting in CC bond activation. Now, with this background, what we are going to look at is we are going to look at another interesting example where there is a competitive activation between a CC and CH bond, and we would see how one dominates over the other. For a particular aromatic moiety of the type shown over here, it has a 3 methyl group and CH2P Me2 This reacts with rhodium chloride PET3 whole 3 at 150 degree centigrade, resulting in a loss of PET3 and undergoing a CC activation, giving the corresponding CC activated product. Okay. So, this is a CC activation occurring as the methyl bond or CC bond between this benzene ring and the methyl gets cleaved, oxidatively add to this rhodium. So, one is over here, the other is over here, and this is the CC activated product. This as CC activation is very challenging, the reaction is carried out at a very high temperature of about 150 degree centigrade. So, this shows that how challenging the CC activation is. Now, as mentioned that there is always a competition between CC as well as CH activations, primarily for the fact that CH bonds outnumbers CC bonds, and in this case too is no different, and that the CH activation is also observed. So, this molecule reacts with the catalyst and loses reacts with the catalyst contain rhodium phenyl and loses a benzene, where the CH of this methyl is lost, gets activated and loses as a benzene. So, here CH activation happens between this hydrogen and this phenyl moiety, leading to the elimination of benzene as well as one PET3 molecule from the catalyst, resulting in this CH activated product. So, what one sees over here, that in this case the methyl CH has undergone activation, resulting in formation of benzene along with this CH2 rhodium bond. So, here is an example of CH activation. Proceeding with a complex which is phenyl rhodium triethyl phosphine, and in the CC activation we had chloro rhodium triethyl phosphine. The only difference being this chloride is replaced by a phenyl moiety for the CH activation reaction. This undergoes, this CH activated product undergoes HCl oxidative addition at very low temperature, giving the oxidatively added product which is this. So, HCl is added on this CH activated rhodium 1 compound, giving the rhodium 3 compound, which at 100 degree centigrade completes the cycle, and this hydrogen protonates and gives back the CC activated product. So, this is a very nice demonstration of how the same product which is obtained by CC activation under very high temperature can also be competitively obtained by more favorable CH activation followed by oxidative addition, and heating oxidative addition product finally would give this CC activation product. So, to note here is that the protonation of this methyl, subsequent cleavage of this results in the rhodium methyl group, which were obtained by direct by CC cleavage. So, this work was done by Milstein, and this is a nice demonstration of arriving at the same product by two different pathways. Now, if one looks at the oxidation state, here the rhodium is in +1 oxidation state, and this is a 16 valence electron complex. In the oxidatively added product, rhodium is in +3 oxidation state, and it is 18 valence electron compound, and this is what one expects if the oxidative addition of CC bond occurs. Similarly, this compound pH rhodium triethyl phosphine, rhodium is in +1 oxidation state, and it has a 16 valence electron. In the CH activated product, rhodium is still in +1 oxidation state, and it still has 16 valence electron. That is because the CH activation has happened over two molecules. One is this, the other is the phenyl group, leading to the elimination of benzene, and similarly the oxidative addition of HCl results in this rhodium 3 compounds having 18 valence electron, which rearranges on heating to give this CC activated compound. So, this is a nice demonstration where two pathways can be utilized, that is CC activation as well as CH activation followed by other, to obtain this CC activated product by two different means. Now, The reason for harsher condition for obtaining this CCA activation comes from the fact that carbon carbon bond or methyl benzene bond in toluene is more difficult to cleave than a benzene hydrogen bond. For example, if one looks at the bond dissociation energy of C6H5 CH3, bond dissociation energy is 427 kilojoule per mole, whereas that of benzene C6H5H, the corresponding bond dissociation energy is much lower at 368 kilojoule per mole. So, these explains the difficulty that we had observed in CC bond activation reaction in our earlier example. Now, we come to an very interesting topic with regard to this activation chemistry, and these are a set of compounds which has very interesting properties, and these are called transition metal perfluorocarbon sigma complexes. Now, so, these are designated by Tm or F, where F is the perfluorocarbon complexes, sigma complexes. Now, one may think that these are quite related to the other transition metal alkyl, sigma alkyl complexes that we have already discussed, but the point to note is that even though structurally transition metal sigma alkyl complex is very much resemble transition metal perfluoro alkyl complexes, but there is a tremendous difference in their reactivity and properties, and that leads us to study these transition metal perfluoro sigma alkyl complexes in greater details. To illustrate my point, for example, for this molecule CF3 cobalt tetracarbonyl in comparison to CH3 cobalt tetracarbonyl, they may look isostructural and they may look that they would be behaving similarly. The only difference that one observed is that CH3 has been replaced by CF3, rest of the molecule remaining the same, and property wise it is seen that there is a significant difference in the property. For example, this molecule can be distilled without decomposition at 91 degree centigrade, whereas the simple alkyl counterpart is very unstable and decomposes at minus 30 degrees centigrade. So, one can see that there is a huge difference in stability when one replaces the hydrogen with fluorine, and that is why the interest in perfluoro transition metal alkyl complexes arises from. So, even though these complexes are very much structurally similar to the transition metal alkyl complexes, their properties are significantly different, and that is what makes them interesting to study vis-a-vis these transition metal alkyl complexes, to understand why and how they behave differently from their related transition metal sigma alkyl counterparts. So, with this in mind, we are going to discuss in more detail the bonding, reactivity and their preparatory procedures that are in place for this transition perfluorocarbon complexes, and compare them with the examples which we had covered for transition metal sigma alkyl complexes, just to see how these differences arise from. Now, by comparing the two examples, what we had seen that transition metal perfluoro alkyl complexes are more robust than transition metal sigma alkyl complexes, and the reason for this is interesting in the sense that because of high lattice energy of metal fluorides, it may seem that transition metal perfluoro alkyl complexes are less stable. However, the stability has other components as well, which arises because of interactions between the transition metal and the perfluoroalkyl moiety, and what it transpires is that this transition metal perfluoroalkyl compounds have greater bond dissociation energy than transition metal alkyl compounds, and which makes the transition metal perfluoroalkane more stable. So, what we have discussed or in this lecture is that these transition metal alkyl perfluoro compounds behave differently compared to transition metal sigma alkyl complexes. Furthermore, what we had seen is that this difference in behavior arises because of higher bond dissociation energy of transition metal perfluoroalkyl complexes with respect to the transition metal alkyl bonds. And we have also discussed in this lecture about competitive CC and CH activations resulting in the same product, where we had seen that CC activation is more difficult than the CH activation and required harsher conditions. However, if these two activations can be judiciously applied on a particular system by varying different reagent as well as reaction conditions, one can steer these two activation reactions towards the same product, and this was finally demonstrated by a seminal work by Milstein, which we had also discussed in this lecture. So, with this I would conclude this lecture, and we will take up the next lecture looking at more details at this transition metal perfluoroalkane interaction, looking at the source of their extra stability by looking at the interaction that occurs between the transition metal and the perfluoroalkyl group, and then we would also discuss the various synthetic procedure available for synthesizing these complexes, and in the next lecture. Till then, goodbye, and hope to see you in the next lecture. Thank you.